So this is Jeff Hamrick at Rhodes College, and I'm going to talk with you about using Scrambling to once again perform a hypothesis test. In this case, a hypothesis test for whether or not the slope coefficient in a simple linear regression model is different from zero. I've got the Brigham Young University body measurement and body fat percentage data already loaded into Fathom, and I've already gone on ahead and I've regressed body fat percentage against body weight in pounds. What we see here is that I have a slope coefficient of 0.162 that appears to be different from zero, but of course that's an estimate based on just a finite sample of 252 data points of the true slope coefficient for the regression relationship between body fat percentage and weight. And so we always want to test whether or not such estimates lend sufficient weight to the idea that for example, in this case, the true slope coefficient is different from zero. And so the way we do that is with a scramble in this particular context. So I right-click on the data box and I create a scramble box. And the parameter that I'm going to scramble either needs to be my Y data, in this case body fat percentage, or my X data, in this case body weight. So I'm going to scramble the body fat values. If I table off of this scramble box and check out body fat as I press the scramble button, they are indeed getting scrambled each time. And what that scrambling does, recall, is it breaks the relationship between the independent and dependent data. And recall that when we shatter the relationship, the bivariate relationship between independent and dependent data, on average the sample correlation coefficients of the scrambled data sets will be zero, and the slope coefficients will also on average be zero. So what I want to do is impose then a measure on this scramble box, and that measure is going to be the slope coefficient computation. So I'm going to call this slope of scramble, and I'll use linear regression slope. My X data in this case are weight, and my Y data are body fat percentage. So for this particular scramble, that slope is indeed fairly close to zero. And of course, now what I want to do is I want to collect this measure for this one scramble box many times, executing many different scrambles. So I'm going to right-click on this and collect measures. 5 measures is not going to be sufficient, but if I shut the animation off and ask Fathom to generate 1,500 measures for us, that should be sufficient. I'll let that run. When we get back, we'll go on ahead and finish executing the empirical hypothesis test. Okay, so Fathom is done generating those 1,500 measures for us. Let's go on ahead and table off of the measures box and then create a dot plot of the randomization distribution of the slope coefficients. So we see that randomization distribution is approximately Gaussian, which is not surprising. Notice that the x-axis is in thousandths, so we're looking to plot a value of our original slope coefficient against these slope coefficients generated by scrambling the original set of data. And we have 162 thousandths here. 0.162 is 162 thousandths. So our original measure plotted on this randomization distribution lies very, 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 very far off to the right, which means our empirical p-value is going to be small. It's going to be less than 1 over 1,500, since we generated 1,500 measures. So that's extremely small. Even if we double it, of course, we have enough evidence to reject the notion that the true association, the true slope coefficient between body fat percentage and weight in a simple linear regression model is equal to zero. Instead, it's something other than zero, and we use a confidence interval construction technique, either calling upon SPSS or doing another randomization procedure, namely sampling with replacement in Fathom to get that confidence interval. Thanks very much.